Good day to all of you. In the last class, we saw how we can go about developing the state space representation of a DC-DC converter. Specifically, we did work using the buck converter as an example. Now, in this class, we shall continue on the same topic of circuit averaging, and we shall consolidate what we learnt in the last class with few more examples and see what we want to do with the state space representation that we have obtained in such a manner. So, this is circuit averaging method continued. Circuit averaging method. We shall continue it. So, in the last class, we had developed the model for the buck converter, which is represented by these two single pole single throw switches and an inductor and the capacitance. By now, you are familiar with the buck converter, which is attached to a load R. This is S1, S2, Vg, and this voltage across the resistance supposed to be V0. Now, here this buck converter is a system where all the variables within it are actually swinging from 0 to some nominal operating point. This is a large signal system having a large signal model. Large signal system, and this has a large signal model. Now, this large signal model is nonlinear. It has a time varying matrix due to the switching character of the two switches S1 and S2. When the switch S1 is on, we have one circuit. When the switch S2 is on, we have another circuit, and these two operating modes come into picture at different points of time during dt and 1 minus dt. So, from the large signal model, we developed the averaged large signal model, and from the averaged large signal model, we removed the steady state model, and having removed the steady state portion of the model, what is left out is the small signal model. Small signal model. Now, this small signal model is the one which is linear, and this is what will be used for control purposes. For all your controller design, you will be using the small signal model. Now, let us revisit something that we did learn in an earlier class. If you remember, we had a transfer curve u versus y, and this transfer curve between input and output could have, let us say, some kind of a characteristic like this, and we have an operating point. And about this operating point, in the neighborhood of the operating point, and let us call this as the neighborhood, we say the system behavior in this neighborhood is linear. In this neighborhood is linear. So, this nominal steady state operating point for an input u, you have a corresponding input y, and for a variation in the input delta u, you have a variation in the output delta y. Now, these two are called the small signal deviations about the operating point. About the operating point, which is the steady state. Or the equilibrium condition. So, we see that the large signal model y is composed of two distinct parts, the steady state part plus a small signal part delta y. Same way, this large signal input u is composed of a steady state part plus delta u. Now, this delta y, delta u, which are the deviations in the neighborhood of the operating point, we have actually termed them with a different symbol in when we were developing the state space representation. We used to call them, if you recall, y hat, and the delta u used to be called u hat. So, therefore, we can say y, the large signal part, is nothing but a steady state part represented by uppercase y plus a small signal part represented by the lowercase letter with a hat on top. So, also you have u, which is having a steady state part u hat, x, which has a steady state part x hat, so on, d, which has a steady state part plus d hat, so on. All these deviations are around here. Now, after having done the small signal model, what do we do with it? We have three models here: large signal model, which is given by x dot, which is equal to a x plus b u. You have the steady state model, which is 0, because uppercase x dot is equal to 0, x dot equals 0 equals a x plus b u. This is the steady state model, and then you have the small signal model. So, in the small signal model, we have x hat dot variations A x hat plus B u hat. So, I have written down only the state equations. Likewise, for the output equations also, you will have these three models. So, this large signal model is actually the one closest to the actual system. It represents the actual system more closely. The steady state model represents the actual system during equilibrium conditions. And as such, most of the time, the system is going to be in the steady state for a large portion of the time, and therefore, your design, the design of the plant is done using these equations. So, this is very, very important, this steady state model, especially for designing the plant itself. So, you would have recalled that design of plant or converter, designing the value of the inverter, designing the value of the C, so on and so forth. Probably in a much later class, we will see how we will use the steady state model to design the converter. And then the third part, the one which we have struggled so long to get the small signal model, is used for control purposes, control design. Control design and also to design the controller. So, for both these purposes, we will be using the small signal model, because should note that it is this small signal model which gives you, this gives you an idea of the dynamics, it gives you the idea of the dynamics, implying that the variations or deviations about operating point and therefore, the controller's job is to see that these deviations are made 0. So, one of the constraints is that the controller design is based on all methodologies where it assumes that the plant is linear. And because of that, we need to have this model especially as a linear model, and which is what it is. In fact, when we do the linearization by neglecting the second order terms of the deviations, basically what we have done is we have linearized it and obtained a linear model, and that is why the values A and B do not have time varying quantities. If you recall, in a more generic sense, we had mentioned that earlier and discussed that earlier. Let me just recap that, because it is pretty crucial that you understand that you have the steady state part and you have the deviations in the neighborhood of the operating point. And if you take y, which is a function of u, which is nothing but function of steady state normal operating point plus terms which contain deviations due to the input deviations about the operating point, nominal operating point. Now, this if you recall, we had used the Taylor series to df by du, deviation of f with respect to u evaluated at u equal to the nominal operating point into deviation u minus u plus 1 by 2 factorial d square f by du square evaluated at the nominal operating point u minus u whole u minus u whole square plus so on keeps going. So, this is nothing but the Taylor series expansion, and out of this you know that these deviations are very small quantities with respect to the operating point. So, they are much lesser than 1, and the square terms will the normalized square terms will be still further lesser than 1, and therefore, the higher order terms above square can all be neglected. If this itself is going to be smaller, u minus u whole cube will be still further smaller, and therefore, all these higher order square terms will be insignificant and we can neglect that, which means out of this Taylor series term, we are only taking this first order term, and that makes it y which is equal to f of u plus df by du evaluated at u minus u. But then in this neighborhood of the operating point, we see that it is linear, and therefore, this is nothing but a constant k. And then when you take the f of u onto this side, it becomes y minus f of u, which is nothing but the steady state quantity, which is equal to k u minus u. So, this is nothing but y hat, the deviations about the operating point, k which is a constant, u hat the deviations of the input. So, this is actually the small signal model, and you see that the small signal model is linear, and this is exactly what we have done in obtaining the small signal model state space representation of the DC-DC converter, where we obtain the average large signal model, and from the average large signal model we removed the steady state portion of the model. And when we were doing the average large signal model and multiplying the various variable terms which contain the uppercase and the lowercase hat terms, we neglected the small signal multiplication terms, assuming that they are insignificant, and therefore, we had only the first order terms, which made automatically the whole system linear. So, this is what you would arrive at. Therefore, if you now go back to the plant, now this is the plant which is having, let us say, let me put it like this. So, from here you have a switch, another switch, inductor, capacitance, and this goes out to the load. This is our buck converter, and here you have your load resistance. Let me maybe erase it here and so that you are able to see properly. This will be the load resistance, and we are going to put the input here. This is V g, this is V naught. Which comes out like this. Now, this is our plant. Now, to this I am going to put this symbolic enclosure, which indicates that this whole thing is the plant. Now, to this plant, we have a control input U, and we have an output to be controlled, which is Y, and somewhere here let us have a comparator plus minus, where you place the reference. This is the feedback portion, and the output of the comparator goes to the controller, and the output of the controller is the control input, which is fed in. This is the structure, the control structure of the plant. Now, what is this control input going to control? Where is it going to go? So, this control signal actually gets amplified. We call it the drive circuit. Okay, drive circuit, and the output of the drive circuit is going to control this switch, and the other switch is actually uncontrolled. It is automatic by virtue of the fact that this can be a diode. So, let us replace that. This will become a diode, and we will have a control switch. So, here let us have a diode, and here let us have a controlled switch like the IGBT, let us say. So, this drive circuit is going to control this. So, you have the drive circuit output giving something like that, pulses. So, whenever the pulse is high, this switch is on. The moment this switch is on, this is positive, this is negative. This positive is going to come to this point, the diode point, and the diode gets reverse biased off. So, therefore, it is off. So, this would be like your first mode of operation, where the supply is directly going to the LC. And in the second mode, when the moment this is switched off, there is a polarity reversal of the inductor voltage, due to the energy storage within it, it will freewheel through this diode. Diode is automatically back into action, it is conducting, and also the switch being intentionally turned off during the 1 minus D period. So, this is the kind of situation that you have, practical situation you have. Now, let us see what the controller is supposed to do. Now, here if you look at this is a large signal, this is a large signal plant. The plant always is large signal, it is existing as a large signal model. Now, out of this large signal model, there are two parts we have split. Here, this is equal to a steady state part plus the small signal part, and the U here that you are supposed to give is containing a steady state part plus a small signal part. So, therefore, here within everything is large signal, but the controller is designed to handle only the small signal or the hat parts. So, the controller is bothered and going to handle only this. So, therefore, the controller is designed to address this, which means what you are feeding back should be only y hat, and what you are getting out of the controller is u hat. So, it is no longer just u, it is u hat, u is within, this is u, it is within inside, which implies that there are two small blocks changes that will happen, and that is one is here and another is here. So, what are those changes? So, let us put a adder or a subtractor, as you may call it, at that point, and one adder or subtractor at this point, okay. And that is what is now considered as the new output, and that is called the new input to the system. So, we will say this is u and this is y. So, as usual, these two are now retain same large signal values, but what you are actually giving to the controller is here. So, the controller is looking at this kind of a model. So, it will change and go like that. So, this red is the plant that the controller is going to look at. So, what do you have here? The output here is nothing but y hat. You need to have y hat, because that is what you can feed back to the controller, because the controller can handle only the small signal. So, controller is always seeing only the small signal model of the system, which means that here you are subtracting, this is plus minus. Can you make out? you are subtracting. Let me make it a bit more clear inside here. The y, the output, large signal output is subtracted. This is plus, this is minus, subtracted from y. Y is the steady state portion. So, large signal minus y, the steady state, is giving you the small signal. Likewise, here you need to add, something, plus, and you need to add the steady state. Now, these steady state quantities are obtained from the steady state model. You know that 0, which is equal to a x plus b u, and you have y equals c x plus d u. Now, the output does not have a direct, as we saw for the case of the buck converter, this is not there. This portion is what we have, and taking these two equations, you can always get y. Let us say, if you know the input u, okay, you can get the x, because from this equation the only unknown will be x, and once you know the x from this equation, you substitute here and get out y. So, that is the y that you will use here. And how do you get the u? From the reference, you have the reference, and from the reference you have the steady state relationship to get u. So, this is an inverse relationship. I will take another color. So, how does it go? Reference is nothing but what you want the output to be, V naught, or what you want y to be. So, y is given, and from y you can get x. So, from x you substitute here, and then you can get u, the reference for the steady operating point. So, this from the inverse equation you can get this, and from the other equation you can get y. So, this way you can use the steady state model to subtract and add and get the small signal values. So, how do we go about? Let us now complete this. Now, here the reference is split into two parts. So, you will have two parts for the reference, which we will be splitting. So, let us say this is reference R. Now, R itself is having a steady state part and a R hat part. So, R hat should be the reference here, and R is what should go to directly to the steady state part. So, there should be something here, and there should be something here which directly takes the R part here and gives it here. So, the steady state part is directly given, the controller is bypassed. Observe that the controller is bypassed for giving the steady state part of the reference. So, this would be the R part of the reference. Now, what should be the R hat part of the reference? So, the desire here is that I should not have a deviation, and therefore, this should be 0. So, this should be equal to 0. There should not be a reference, there should not be a deviation for the reference. So, y hat should eventually be such that the controller should take care that y hat should eventually reach 0 by making this error E equal to 0 every instant of time. That would be the job of this controller, to make y hat 0. Then the whole system will be at the equilibrium state as provided by this reference R, which is going through this steady state portion. So, this will be the structure of the controller for any converter for that matter, though we have specifically taken this DC-DC or the buck converter portion. So, if you look at the issue of the controller design, it boils down to designing this controller for a small signal model as shown by the red. Now, in this case, for the buck converter, the input U, what is the input U? The input U is nothing but the deviations of the duty cycle. So, here you are going to give the trigger to the switch, and what is it that you will give trigger to the switch? It is the duty cycle D. So, if you keep on erasing these things and see, replace it by appropriate. So, for the appropriate symbols. So, for the converter here, this will be the input U, control input U, D, and what will be the steady state, and what will be the small signal. This will be small signal D, and this will be the uppercase D. So, you get a D duty cycle, which then passed through appropriate ramp and drive circuit, will give you the signals for switching on those devices. What will be output y hat? So, the outputs here, see the output here would be V naught, here is uppercase V naught, here it is lowercase V naught hat, because you want to control this, the output voltage. So, coming back here, we see that this becomes V naught hat, and what are the references? So, the references also change in symbol. So, this will become V naught ref. The value is 0 for the R hat portion, and this would become V naught ref for the steady state portion. So, the steady state portion passes through like this and affects directly the D. by a scalar here, and this gets scaled multiplied by 0 to provide as the 0 reference to the deviation portion. So, this will be how the controller setup will look like. The moment there is any deviation about the operating point, that will mean that this will be non-zero, V naught hat will be non-zero, that will go as a feedback, it will compare with 0, error will be non-zero, controller will take an action, D hat will be provided, which will get added to the steady state portion, goes into the consolidated duty cycle, value goes into this trigger, control trigger, and gives the control input, which will bring the V naught to its normal value. So, this is how the controller operation will happen. And for any other converter, this portion will get replaced by that particular converter. Okay. So, this is basically the framework in which we will be trying to operate all the DC-DC converters. So, now what we do in the remaining time today is to work out one example completely from scratch, that is, we start from the basic DC-DC converter circuit. We develop the state equations for the different modes, combine them, have the average large signal model. From the average large signal model, subtract the steady state model, and from the from that you have the next step, which is the small signal model. So, that would give you the, and then identify the control inputs. Up to this point would give you the state space representation of the complete controller. So, we would like to go through that step for another converter, let us say the boost converter for now. I have worked it out here and I have the sheet with me, so that it will help in going smoothly. I will not do the working here, you will have to work it out separately by yourself, but I will try to give you the in every step the final answer, so that we are not deviated in deriving and working, but rather to see the flow of how we go about getting it. Okay. So, let us begin by working on this particular thing, which is a boost converter, and we will do it step by step for this and work through the different process of circuit averaging. So, boost converter, we are going to obtain the state space representation by circuit averaging method. So, this is what we want to do, this is our goal, and to this end we will do that. So, first the circuit. The circuit is simple, you know that you have VG, you have the inductor, and at this node point you have one switch, you have another switch here, you have C, and you have the resistors there. Have the resistor here. So, this is, we call it a switch 1, this is switch 2, R, C, L, V G and V naught. Now, this can also be written in circuit form, that is circuit representation of the switch symbols L, and this can be a MOSFET, transistor, IGBT, any of those, and switch 2 S2 will be a diode. You have C and R. This is your R, L and Vg and V naught here at the output. So, this is the representation in the circuit form. Okay. Now, to this we need to go about getting the equations. Here we could also make a bit more generalization by at the output we have V naught, and let me make some space here. Let us have connected to this a current source, because the voltage output V naught at this point is constant. Anything divided by R can effectively be replaced by a constant current source flowing like this, and we can label it as I Z just for convenience. This load can be replaced by a constant current source I Z, which is equal to V naught by R value. So, effectively it would look like as though it is like that. Okay. So, these things can also be done such that any value of R you could keep changing, and only the I Z value will change, because V naught is being controlled and we are trying to maintain the value of V naught, or it is a constant value. Okay. Now, this is also a possible thing in literature. You will see such a practice also. So, from here we start our writing down the state space equations. This is conducting, this is on during the time, this is on during the time dTs, this is on during the time 1 minus dTs. Okay. So, during the time dTs, if you look at the equations, it is like this. This is the framework. I am going to put in the matrix framework first, and then let us fill in the places. Okay. So, like that, plus I will consider another, you will know. So, let us say for example, that we have a system like that. What are the states? The current I L and the voltage V C. These are the two states, and V C is nothing but V naught. So, you have I L dot V C dot. Now, I am populating this, you can work it out. It will be something like this. You have I L V C 1 by L 0, you have V G as the input. Now, if you consider the current source as another input, that could also be put in there, 0 minus 1 by C. So, this is the state equation during the time dTs, and during the time 1 minus d Ts, you would have IL Vc dot 0 minus 1 by L 1 by C minus 1 by RC IL Vc dot Vc plus 1 by L 0, you have Vg plus 0 1 by C minus 1 by C, and Iz if that is also one of your control inputs. Okay. Now, to both these cases, what are the outputs? What are the possible outputs that you could have? These are the state equations. So, I can put that in bold, state equations. Now, let us come to the output equations. Now, for the output equations, let me go back here. One possible is this, V naught can be an output. Another possibility is to control the input current itself, Ig. In unity power factor converters, where they use the boost converter topology, Ig is normally controlled. Okay. So, you could have that as the output variable too. So, during this time, you can have output is V naught, one of them, 0, 1, you have IL Vc. This is one output equation, or I could also have another Ig, which is equal to 1 IL Vc. You could also put it in the matrix form as V naught Ig equals 0, 1, 1, 0 like this, and IL Vc. This is, and for the case of 1 minus dTs, the output equation V naught and Ig are the two outputs, possible outputs, and comes like this. So, these are the output equations, output equations. Now, after having developed the output equations, we need to develop the averaged large signal model. So, in the averaged large signal model, what do? We are trying to combine the two modes, operative modes during DTS and 1 minus DTS, and obtain the equivalent values. So, if you see here, A would be A1 during DTS into D plus A2 into 1 minus D. This is what we would be doing. Likewise, you have for B, which is equal to B1 D plus B2 into 1 minus D, so on. C1 D plus C2 1 minus D. And these are the generic rules that we saw how we combine them. So, if you combine them, the average, that is A1 is nothing but, here I will write it A1, and this is B1. You could apply for this and this together. This is A2 and B2, this column and this column taken together, and for the output equations you could take this one as C1, C2 and D1 equals D2 equals a 0 matrix. So, applying those, applying all these relationships, we will get the average large signal model as follows. You have I L derivative, V C derivative, which is equal to 0, 1 minus D by E L, 1 minus D by C, minus 1 by R C. This multiplied by the state vector x, plus you have the two inputs 1 by L and 0 for the V G input, plus 0 and 1 by C for the I Z input, load as an input. I Z is nothing but the load, we call it the load as the input. And one of the outputs you could have V naught and I G as the other output, that is what we had considered, equals 0, 1, 1, 0. This is the C matrix and I L V C. So, this is your averaged large signal model, averaged large signal model. Observe that A matrix, B matrix together, these two together, this is one column, this is the second column, C matrix, D matrix is not there because this is 0 plus U. And as such, we are not using that, we will not use it. Observe, you have a D term, time varying D term, D which is a large signal value there, which is composed of the steady state uppercase D plus D hat. You have a D plus D hat. So, A matrix becomes time varying, and as such you can't use it directly for controller design applications using the linear time invariant approaches. So, the A matrix is a time varying matrix, which we need to convert it into a time invariant matrix, and that is the job of linearization. wherein we remove the steady state part, linearize it and consider d hat as another input, because d hat is a control input. We want it to come here as a control input. Then the A matrix will become a time invariant matrix and the state space representation becomes amenable for controller implementation. So, I will at this point of time ask you to practice what should come further. How do you go about doing the linearization? By removing the steady state part and removing the higher order small signal deviations, and then arrive at the small signal linear small signal model. Try to do that as homework. In the next class, next session, we will continue with this and see how we obtain the state space representation of the whole system. Thank you.